Now, as we continue with functions, this is a definition that starts off with, given the function f that maps the set A into the set B, the set A is the domain of f. Every element in A will get mapped to an element of B. The function B is called the codomain. It is not necessarily the image of f or the range of f. But we can make one statement. The codomain of f is a subset of B. So the collection of elements that f maps A to, they live inside of B, but it may not be all of B. Frequently, the image of B is hard to find. So frequently we'll say, oh, I've got a function that maps the reals into the reals, but maybe not to every single real number. Let's take a look at an integer function. Given f that maps all of the integers into integers. Oh, I'm sorry, I'm going to use natural numbers. I want positive integers. Natural numbers into natural numbers. Find the image of f. Find the image of f given that the function itself is f of n equals 5n minus 4. So first let's observe that this function does operate on all of the natural numbers. We're allowed to plug in any natural number because we can multiply any natural number by 5 and then subtract 4 from it as well. Well, this is fairly simple. The image of f, let's just start the list and see if we if we can get a pattern going. Well, let's start with 1, the first natural number. When n is a 1, you have 5 times 1 minus 4, which is 1. Then we move on to 2. When n is 2, we get 5 times 2 is 10, minus 4 is a 6. Then n becomes a 3, so we get 15 minus 4, which is 11. And then we move on to 4, which is 20 minus 4, which is 16. And I think we can see the pattern from here on out. 1, 6, 11, 16, 21, 26, 31, 36, and so on. Oops. It's the image. The image of f is this set, a subset of the natural numbers. Now, a set that's related to f is the converse. Soon that will become the inverse, but let me write this definition of the converse of a relation. The converse of a relation f is f with a hat on top of it. That's just the terminology, or that's the symbol used for the converse of f, where the converse of f is equal to a collection of ordered pairs, x, y, such that it's all the ordered pairs x, y, where yx is in f. Now these x and y's are dummy variables. I could have said y comma x such that x comma y is in f. It's just the set of ordered pairs taken from the relation f, and you switch the first and second components. That's all we're doing. So again, I could have written this like the set of all X such that XY is in F. These two are exactly the same thing, and that's the converse of a relation F.